So this is the fifth video in my series on causal inference, and this one's going to focus on randomized control trials. And this is where it gets interesting because now we're talking about how basically true causal effects can be found using just observed data with some strong assumptions as opposed to having to use hypothetical data. And again, just acknowledging this book, What If, by Miguel Hernan and James Robbins, which has guided this lecture series. So we started with this diamond pickaxe, this potential outcomes framework that's been the focus of previous videos. I'm going to skip over experimental lab-based just because that was covered in the first video and it would kind of disrupt the flow of progress of the series. And now we're going to look at the iron pickaxe. We're going to look at experimental randomized control trials. So surgery and mortality is what we're looking at surgery or antibiotics and who lives longer after 1 year. Prognosis is basically an issue here. It's a confounder. It's obviously related to mortality just because by definition prognosis is how likely someone is to do well or not do well in their disease progress. But it's also related to whether they get surgery or antibiotics. And that's because in the real world, the way things go is when someone arrives with a poor prognosis, the doctor takes this into account and that informs whether they assign them to treatment or surgery or antibiotics. So let's just say the surgery is invasive and reserved for those with a poor prognosis. This individual is probably going to end up in the surgery group. Conversely, someone with a regular prognosis might be more likely to end up in the antibiotics group. And we end up with these two groups that aren't exchangeable because the surgery group has way more people with a poor prognosis than the antibiotics group. And basically, let's say we find that way more people die in the surgery group. It's hard to say if that's because they got surgery or because there's just more people in that group with a poor prognosis. Randomization gets rid of that relationship between prognosis and treatment status by making the decision of which treatment group the person ends up in random. So if there's two treatment groups, this is like flipping a coin, where this person with a poor prognosis is equally likely to end up in the surgery or antibiotics group, and in this case they end up in the antibiotics group, and this individual with a regular prognosis is equally likely to end up in either group. And in this case they end up in the surgery group. And what this ends up with is two fairly exchangeable groups. They aren't perfectly exchangeable in this case. In surgery, we have 5 individuals with a poor prognosis and 4 in the antibiotics group. It's much more exchangeable than it was, basically. So association can equal causation in a randomized control trial. That means whatever effect you find in a randomized control trial can be considered causal as long as some assumptions are met, such as including no lost follow-up, full treatment adherence, one version of treatment, and double blinding. So just to illustrate no lost follow-up, let's just say we have these two groups, chemo and radiation, both with 100 people, and we're following them for 5 years. But partway, 25 people in the chemo group stop showing up to appointments, possibly because they're too sick to travel to those appointments and have chosen a closer doctor that isn't part of the study. Then all of a sudden, the 75 people in the chemo group that are left are a healthier subset, and the two groups are no longer exchangeable with respect to whatever baseline health characteristic led those 25 people to leave. Full treatment adherence is another one. Now, 100 people in the exercise group and 100 people in the no exercise group. If they're followed for 5 years and 25 people in the exercise group choose to stop exercising, so cross over to the other arm, now we've effectively allowed these 25 people to choose their own treatment. The only thing that makes randomized control trials different from an observational study is people don't get to choose their treatment in the randomized control trial. And when these people jump from the exercise group to the no exercise group, they've effectively chosen their own treatment and kind of muddied the distribution of whatever underlying health behavior might lead them to make that decision, basically. And then the exercise group ends up a healthier subset again and no longer exchangeable. Following that same exercise example, one version of treatment is this assumption of consistency. And what that would look like is if 25 people in the exercise group began exercising half as much, then all of a sudden we'd have two versions of exercise. We'd have like 2 hours or an hour of exercise a day that was prescribed, and then another version where people are exercising like half an hour a day. And that makes it very difficult to interpret a treatment effect when there's more than one version of the treatment. And double blinding is another one. It's important to blind participants, and what that means is they don't know whether they're in the placebo or the treatment group, because if they know they're in the placebo group, they might blow whatever negative things they're feeling out of proportion. If they know they're in the treatment group, they might basically have a better outlook on their situation. Similarly, if researchers know which group someone's in, they might have that might basically influence how they interpret how well that person's doing. So when these four assumptions are met, we have exchangeability. And what that means is that if we were to switch which group of people got the treatment and which group of people didn't get the treatment, we'd get the exact same causal effect. And the formal notation for exchangeability, here I like these this here on the left. At the top, we have the probability of the individual getting the outcome if they were treated, given that they were actually treated, and the probability of the individual getting the outcome if they were untreated, given that they were actually treated. That can be kind of encompassed by this y subscript a, without it being equal to anything. And when we say y subscript a, we're basically saying whatever we're talking about applies to both potential outcomes, the a equals 1 and a equals 0. And similarly, the conditional for when the individual in reality is untreated would be the same, except the thing on the right side of the given vertical line is that the individual in fact was not treated. The notation is hard to interpret, but if you bear with me, there's visuals that will help. And marginal, the only real difference here is we don't pay any mind to the actual treatment that an individual is receiving. It only looks at the realm of potential outcomes. And again, this y subscript a just encompasses that whatever that statement is talking about applies to both a equals 1 and a equals 0. So exchangeability means that this probability of the outcome, given that the person is treated or untreated, is the same, basically, because we have probability just on the left side of this equal sign. We have y subscript a equals 1 given a equals 1, and that whole thing is equal to when a equals 0, so we can just get rid of the a equals, because the situation is the same regardless of whether the person actually was treated or actually was untreated. And once we get rid of the a equals 1 and the a equals 0, both of these things are just equal to the marginal probability of the outcome. So what that means is the potential outcomes, like the potential outcome of them getting the outcome given that they were treated or untreated, is independent of what they actually got. And so it'll help just to see this visually. How I think about this is this y subscript a on the left. When this individual is treated, they don't get the outcome, and when they are untreated, they turned red, they got the outcome. And that's something that is this fixed, it exists independently of what they actually get. So if they get the treatment, a equals 1, everything on the left stayed the same. Nothing changed as a result of what they actually got. This kind of preordained, if they get treated, they don't get the outcome. If they don't get treated, they get the outcome. That exists regardless of whether they don't get the treatment or whether they get the treatment, basically. Another way to say that, and this is where it kind of came home for me, is that this is the specific situation where the probability of the outcome when the individual is treated is equal to the probability of the outcome given that the person is actually treated. What drove that home for me is that basically this statement at the bottom, if you just read it a couple times, it might help. So the proportion of those that are disease positive in the treated group, so in this observed data, this conditional regular data, is the same as the proportion if everyone had been treated. Like if we had this population where, regardless of what group you were assigned to, if everyone was treated back into this hypothetical realm, we'd have a probability of the outcome, so just the number of people diseased. Basically, that marginal probability of the outcome is equal to what we actually observe in those who were actually treated. Yeah, that one was a little harder to explain, but I've done this a couple times, and I think that's the best I can do. I hope that was helpful.